Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll study the second important concept for functions, that is differentiability of a function. In 11th class, we've already studied what the derivative is, or the differential with respect to x is. I'll just do a brief recap of that, and then we'll study the concept of differentiability. So if y is equal to f of x is a function, then the derivative at a single point c is written as df by dx at x is equal to c, df of x by dx at x equal to c, and is given by limit delta x approaches 0, f of c plus delta x minus f of c by delta x. Delta x is a change in x, and as the change in x goes to 0, or another way of saying this is that this point goes to c, c plus delta x goes to c. If this limit exists, then this is called the derivative of f at c. Then instead of a single derivative at a point, you can actually calculate the derivative of a whole function over a region, and that is given by df by dx, which we'll also write as f dash of x. Dash denotes the derivative with respect to the argument, in this case that is x. This is equal to limit delta x goes to 0, f of x plus delta x minus f of x by delta x. Then in 11th class we saw derivatives of some standard functions. The derivative of x to the power n, which means d of this by dx, is n x to the power n minus 1, and the derivative of sin x is cos x. The derivative of cos x is minus sin x. The derivative of e to the power x is e to the power x, and so on. Right. Then we studied some properties of the derivative for two functions, u of x and v of x. U plus v dash means the derivative of u plus v is equal to u dash plus v dash. U minus v dash is equal to u dash minus v dash. The derivative of the product of the two is equal to u v dash plus u dash v. That is the first function multiplied by the derivative of the second function plus the derivative of the first function multiplied by the second function, and u divided by v derivative was u dash v minus v dash u by v squared. And finally we had the chain rule, which said that d of f of x by dx can always be written as d of f of x by some other variable y multiplied by dy by dx. So these were the rules we saw. Just also for a recap, for the sake of it, I'll just do one simple example of the chain rule. If f of x is the composition of two functions, let's say sin x and x squared, then it is sin of x squared. Then df x by dx can be written by the chain rule as d of f of, I'll just write the actual value, d of sin of x squared by, now y will take it to be x squared because that is the argument of the function inside, into d of x squared by dx, which gives us d of fx by dx is equal to, now x square can be substituted to some other variable t here, so this is d sin t by dt. That is the derivative of sin t, which is cos t or cos of x squared, and this is multiplied by the derivative of x squared with respect to x, which is 2x. So we discussed this in 11th class, but we assumed at that point that if we are differentiating a function, that means the limit actually does exist. right? When we say that f dash x is equal to limit delta x goes to 0 f of x plus delta x minus f of x by delta x, or when we say d sin x by dx is cos x, where the derivative would be defined in this similar fashion. The moment we say the derivative of this function is that function, we are already assuming that the limit exists. But now we'll study the more general concept of whether or not the limit actually exists. So for any function f dash x, for any function f of x, if this limit exists, then that function is called a differentiable function. Now every function whose derivative you know is by definition a differentiable function because it has a derivative whose value you know, right? But there are some functions for which the derivative does not exist. So I'll start with one example of a function whose derivative does not really exist, and that function is the modulus of x. This is the graph for modulus x. We saw this in the previous video. Now just by the figure you should be able to tell it's not differentiable, because if this limit exists, that means this limit has to exist from both the left side and the right side. Right, in this case it's for particular x, here x is 0, but if the limit exists, it has to exist from both this side and this side. Right, we are calculating it at x is equal to 0. But you can see from this side the limit is denoted by the left hand derivative, and that is negative. But here it is positive. So obviously the limit does not exist. Let us look at that explicitly. The left hand limit, I'll just write it as left hand derivative at any point c, in this case c will be 0, but I'll just write the general formula, is denoted by f dash x plus, so this, sorry, minus, left hand is minus, right hand is plus, right, and this is given by limit delta x goes to 0 plus, now we are making sure that it goes from the correct side, f of x minus delta x minus f of x by minus delta x. Basically we are going from this side, so by the original formula delta x would be negative, we want it to be explicitly positive, so we replaced it by minus delta x in these two situations. And the right hand derivative is given by, we are talking at a particular point c, so I'll just write it as c here. The same goes for the general x as well. F dash plus of c, which means the right hand limit is, now notice in both cases delta x goes to 0 plus, and because there's a minus sign in the first one, we've ensured that the first one is the left hand limit where we go from the left, and the second one is the right hand limit. Minus f of c by delta x. So let's use these two formulas for fx is equal to mod x. Mod x is defined as x if x is greater than or equal to 0 minus x if x is less than 0. Right. So for the left hand limit, we'll be going from the left side, so fx will be minus x. So f dash minus of 0 will be given as, just look at this formula, limit delta x goes to 0, f of c minus delta x, c is 0, so f of minus delta x, right? But we already know that for negative it is minus x, so f of minus delta x will be delta x. So delta x minus 0 by minus delta x, which comes out to be minus 1. In fact, the derivative, and in fact for x less than 0, this is basically y is equal to minus x, which does have the slope minus 1. What is f dash plus of 0? Limit delta x goes to 0, f of c plus delta x. C is 0 here, so f of delta x, which for positive x is delta x minus 0 by delta x, which gives us 1, and we know that the slope here indeed is 1. So the left hand slope or the left hand derivative at the point x is equal to 0 is minus 1, but the right hand derivative is 1. Therefore the limit does not exist. Right? So we will say that fx is equal to mod x is not differentiable. At x is equal to 0. Now notice that it is continuous. We saw that in the last video. Continuous is the condition which implies that you should be able to connect them. That means you should not have to lift the pen from the paper. Differentiability means that it will be smooth. So this will be a differentiable function because at this point both the limits go to 0, but here the limit here and the limit here do not go to the same value. So anytime you have cones, you have cusps, you have angles, in those cases the function will not be differentiable. Even if you have a graph like this, this is not differentiable, but if you have a graph that goes gradually like this, then it is differentiable. And every function that you've known the differential of, x to the power n, sin x, cos x, e to the power x, log x, since you know the derivative, that means they are differentiable. Now another concept here is very similar to that one in the previous video. A function, previously we saw the definition for differentiable at a point. Both the limits should exist. Now we'll talk about differentiability in a region. A function f of x is said to be differentiable in a region a to b, both close brackets means both are included, if it is differentiable at every point in the region. Right. So this is the same as that for continuity. We first defined continuity at a point, then we said the function is continuous in a region if it's continuous at every point in the region. Similarly, we defined differentiability at a point, that is the limit x approaches from the left or the right, provided both the limits exist and are the same. And now we've provided the function for the definition for differentiability in a region. And again, there is one small trick here which is similar to that for continuity. For any point C which is between A and B, we will need to have f dash of x at C is equal to limit delta x goes to 0 f of x plus delta x minus f of c minus t, f of c plus delta x minus f of c by delta x, positive. This is the right hand limit. It should be the same as the left hand limit. F of c minus delta x minus f of c by minus delta x. They both should be the same, right? And they both should exist, obviously. But let's look at the graph. This is point A, this is point B. Both the points are included, but they are the end points. So let's say the graph is something like this. Then obviously the function is not defined, or at least we are not considering the function to the left of A or to the right of B. So for A we only need the right hand limit, and for B we only need the left hand limit. That means f dash of x at A should be equal to only the right hand limit. Delta x goes to 0 plus f of a plus delta x minus f of a by delta x, and f dash of x at B here should only be the left hand limit. We don't need to consider the right hand limit. So here the limits don't need to be equal to anything, they just need to exist. Limit delta x goes to 0 plus f of b minus delta x minus f of b by delta x. Notice here the function is at a plus delta x, where it is actually defined, and here it is at b minus delta x, where it is also actually defined. So these three conditions need to be true. These two limits need to be equal. Both these limits need to exist for us to say that a function is differentiable within a region. Now, differentiability is a stronger condition than continuity. And the reason for that is that a differentiable function is always continuous. So I'll just draw a couple of figures first, and then I'll try to prove this mathematically. This is a function which is continuous and differentiable, right? At this point, if you look at it, both the limits for the derivative approach 0. So this is continuous and differentiable. On the other hand, this function is continuous, but it is not differentiable. So it is not necessary for a continuous function to be differentiable, but a differentiable function necessarily has to be continuous. Let's take a discontinuous function. This is a discontinuous function, right? Now this function cannot be differentiable because it is not even continuous. If you look at the right hand limit here and the left hand limit here, they are obviously different, right? So this is a function which is not continuous, so obviously it cannot be differentiable. On the other hand, if you join those two, now the function is continuous, but it is still not differentiable, right? And obviously you can just take the standard case, the same case we took here actually, where you can have a function which is both continuous and differentiable everywhere. So if it might not be continuous, then it's definitely not differentiable. But if it is differentiable, then it has to be continuous. So being differentiable is a much stronger condition than for it to be continuous. Let's try to prove this now. If the function is differentiable at a point C, then we know that f dash of C is equal to, I'm sorry, I keep writing x, is equal to limit delta x goes to 0, f of C plus delta x minus f of C by delta x. And these are now it's not 0 plus, now it's 0, so delta x can be positive or negative, which means we can go from either the left or the right. So its value is equal to f dash C. Let's say that is some value k. Obviously it cannot be infinite because the limit exists. It's some finite quantity k. From that we get limit delta x goes to 0, f of C plus delta x minus f of C is equal to limit delta x goes to 0 k delta x, right? We took delta x to the right side. Now we know what this is. Since k is a finite number, it is not infinite, this right hand side is 0. So the left hand side is 0, which tells us that limit delta x goes to 0, f of C plus delta x is equal to f of C, which is the definition, if you look at the previous video, for a function to be continuous, that the limit of the function's value should be the same. For derivative, the limit of the derivative should be the same. For continuous, the limit of the value of the function should be the same. Right. So a differentiable function is always necessarily continuous. Now we've seen how to differentiate many basic functions when we learned differentiability in 11th class, when we learned calculus or basic differentiation in 11th class rather. Now that we've learned the concept of differentiability, we can try to differentiate some advanced types of functions. So the first topic we'll study is the derivative of an implicit function. So what is an implicit function? Most of the time we are given the function in the form of y is equal to f of x, and then you can differentiate this directly and get dy by dx is equal to whatever the formula is, limit delta x goes to 0, f of x plus delta x minus f of x by delta x. Or you can use some standard formulas and you get the values. But a lot of the times the function y is not given, it's not given in a way that just y is on the LHS and only x is on the RHS. Sometimes we are given a function of x and y. For example, you might be given x square plus 2y minus xy is equal to 0. Right? Or you might be given x minus y minus pi is equal to 0. Right? Or x square y plus x cube y cube minus 3y squared x is equal to 9. So these are functions in which obviously y depends on x. For every value of x, you have a value of y. So y does depend on x, but it is not given in the form that y is on the LHS and a function of x is on the RHS. Now in many of these cases, we can actually manipulate this form of the function and get it into our desired form y is equal to fx. For example, this function can be written as x squared plus 2 minus x times y is equal to 0. So what we'll get is y is equal to minus x squared by 2 minus x. These two equations are the same because these two equations give us the same result. Similarly, in this case, you can get y is equal to x minus pi. In this case, it might be somewhat more complicated. I just wrote down these formulas off the top of my head, so we don't need to do that. This concept is what is important. Up till now, we've gotten functions in the form of y is equal to fx, and from that we've used this formula to differentiate them. But what if instead of y on the LHS and only x on the RHS, what if we had a whole combination of x and y on both the LHS and RHS? These forms of a function are called implicit functions, and the explicit functions you've already seen are called explicit. So explicit means basically that the function has been defined explicitly as y as a function of x. But sometimes you have implicit functions and it may not always be possible to solve for y in terms of x. So now our goal is to try to learn to solve the derivative of an implicit function. So there are generally two ways to solve the derivative of an implicit function. One is what you would already do had I not told you any of this. You manipulate it and solve for y as a function of x and then differentiate. For example, if we take the simple example x minus y minus pi is equal to 0, from that we can get y is equal to x minus pi, and from that we can differentiate to get dy by dx is equal to 1. Right, so this is one way. But if it is not possible, then the second way is differentiate both sides of the implicit relation. So when you differentiate both sides will have both x and y. Any derivative of x or a function of x you can directly write. For example, if you have x cube or sine x or sine of x square somewhere, you can directly differentiate it. Anytime you have a function of y, for example sine of y squared, right? So you can write it as, let's just take sine y for now, y squared might be a little bit extra complicated. So if you have sine y somewhere and you differentiate it, another thing I forgot to mention here, differentiate with respect to x. So both sides should be differentiated with respect to x. So when you have this side differentiated with respect to x, you can, by the chain rule, write it as d sine y by dy into dy by dx, which is basically dy by dx cos y. So all functions of x will give a new function, all functions of y will give you another function of y, but also will give you a term of dy by dx. and then you can solve that relation algebraically to get dy by dx. If we did that in this equation, what we would have done is, the RHS obviously would be 0, we'll differentiate the LHS with respect to x. So we'll get d of x minus y minus pi by dx is equal to d of 0 by dx, which is 0. Which gives us, now we'll differentiate this function, the derivative of x is 1 minus the derivative of y is dy by dx, and minus the derivative of pi is 0 because pi is a constant, so this is equal to 0, which gives me again dy by dx is equal to 1. The good thing about differentiating in the implicit way is that it does not always give you an answer in the explicit way, nor do you always want it, because you will have functions of x, dy by dx, and functions of y. The derivative will also be given in an implicit form. So let's look at another example. Let's say y plus sine y is equal to cos x. Now it would be hard for us to get this function in the form of y is equal to f of x because you have y and sine y both here, but you can differentiate this in an explicit way. If you got it like this, then you can directly differentiate it, but let's say our goal is to get dy by dx. So what you can do is differentiate both sides with respect to x. So d of y plus sine y by dx is equal to d of cos x by dx, which gives me dy by dx plus d of sine y by dx is equal to the derivative of cos x is minus sine x. Now this term we can write it as dy by dx plus d of sine y by dy into dy by dx. So we get cos y dy by dx is equal to minus sine x, and from that we can get dy by dx is equal to minus sine x divided by 1 plus cos y. So we didn't get dy by dx directly as a function of x, but we did get dy by dx, and in a lot of cases this would be enough for us to move forward. So this is one type of differentiation that you can see. There's another type of differentiation. We've already seen exponential and logarithmic functions before, but if you take one function to the power of another function, you can differentiate that using logarithms. So let's say you have y is equal to f of x, which is a function of the form of u of x to the power of v of x. Right. Let's say it could be x cubed plus 3x squared to the power of x squared minus 5. How do you differentiate a function like this, where x is also in the exponent? Well, we can write this function as e to the power times v of x ln u of x. Now I'll not go into the details of exponential and logarithmic functions here because we've already seen in the 11th class, but we know that e to the power vx ln u of x will actually be e to the power of ln ux to the power vx, which will be ux to the power of vx, right? Or we can just directly differentiate both sides here. Y is equal to ux to the power of vx. We can take logarithm directly here, which gives us ln y is equal to ln of ux to the power vx, or v of x ln u of x. You can see that this equation and this equation is exactly the same, right? If this is true, then y is e to the power of this. Now you can differentiate both sides, and what you'll get is 1 by y dy by dx is equal to v of x times the derivative of this thing by u of x u dash of x plus ln u of x times the derivative of this thing, which is v dash of x, right? And dy by dx would be y times this, where y you can substitute from this value. So dy by dx will be this multiplied by y, or multiplied by u of x to the power v of x. right? Anyway, you don't need to remember these complicated formulas. All you need to know is ux to the power vx can be written in this way. And after this is just a matter of following the already known rules of calculus. Another type of function we would like to differentiate is a function in a parametric form. So if you have y is equal to f of x, that means for every x there is a particular value of y. But sometimes what you can have is both x and y can depend on a third variable t. Let's say x is equal to f of t and y is equal to g of t. From eliminating these two equations, you can always get the relation between x and y. For example, just let's say x is equal to t square minus 2 and y is equal to t plus 4. If these two were true, this is x as a function of t and this is y as a function of t, then obviously we can get y minus 4, which is t, whole squared is equal to x plus 2, which is t squared. Right? Or you can say this is the square root of this and you can add 4 to this and you can get y is equal to this. So now you've gotten the function in the explicit form, y is equal to root of x plus 2 plus 4. Right? So this is what I'm trying to say. Y is equal to f of x means for every x there's a value of y. What if for every t there's a value of x and for every t there's a value of y? That also means that for every x there's a value of y. So if we know x and y in this form, then either we can manipulate these two to get y as a function of x and then differentiate, or what we can do is dy by dx is equal to dy by dt divided by dx by dt. Right, dt will cancel and we'll get dy by dx. So for example, in this case, what is dy by dx? If we were to get it from here, 4 will not have a derivative, root of x plus 2 will give us 1 by 2 root of x plus 2. What does this turn out to be? X plus 2 is t square, root of that is t, so it is 1 by 2t. But we can get that from this formula. What is dy by dt? dy by dt is 1. And what is dx by dt? It's 2t. Right. So when you have, instead of y is equal to fx, you have this, you can either eliminate t to get y of fx and then differentiate, or you can simply use this formula and differentiate. In both cases, you will get the final same answer. Finally, there are two theorems which are left in this chapter, the Rolle's theorem and the mean value theorem. So let us discuss that now. We will not be giving the proof of these theorems as they are not in your course, but the theorems themselves will look to you to be quite intuitive. So Rolle's theorem says, let f, which goes from a comma b to r, that means the domain of the function is a comma b, be continuous and differentiable on a comma b. So we have a function whose domain is a comma b, and we are given that it is differentiable and continuous in this domain, and also what we are given is f of a is equal to f of b. That means the value of the function at two endpoints, let's say this is a and this is b, so both of them have the same value of y. F of a is equal to f of b. In that case, there exists some of c between a such that f dash of c is 0. So if you have a function defined in a region and the value at the two endpoints is the same and it is continuous, that means there must be some c such that the derivative is 0. So let's take first the obvious case. You go directly here, which means it is constant. Obviously 0 for every c. Any other form, whether you go like this, or you go like this, or you go like this, it doesn't matter. You will need to have at least one point where the derivative becomes 0. And that is what Rolle's theorem says. If the value at the two endpoints is the same and it's continuous, remember it has to be continuous. Otherwise you could have this is A, this is B. You could have a function like this, in which case the derivative is not 0 anywhere, right? Or like this, in this it's not continuous or even, right? So that's not allowed. If it's continuous and differentiable and the value at the two endpoints is the same, then the derivative has to be 0 at some point in between. This is called Rolle's theorem. And the next theorem is an extension of the Rolle's theorem, which is called mean value theorem. The conditions for the mean value theorem are the same. F from A to R is continuous and differentiable in the region A, B. Then, now there is no f of A equal to f of B here. It is quite simply, there always exists some C between A and B such that f dash of C is equal to f of B minus f of A by B minus A. And this, as if this is A and let's say this is B, no matter how you go, will be this in them. No matter how you go, there will always be some point which will be the same as this line. No matter how you go, some point which has the slope the same as the line joining A and B. And you can see if f of A is equal to f of B, then the RHS is 0 and we have some point C such C is. So the Rolle's theorem is actually a special case of this mean value theorem. Let's just, to apply this, try to verify both of them for some functions. Let's try to verify Rolle's theorem for y squared plus 2 in the region minus 2, 2. 2x is 0 and we can see that this point equal to as indeed between minus 2 and 2. Let's see mean value theorem for y is equal to x squared in between 2 and 4. So we know that there must be some function such that f dash, some point C such that f dash C is f of B minus f of A by B minus A, which is, if we put in 4 here, 4 square is 16 minus 2 square is 4 divided by 2, that is 6. So we know there must be some C such that f dash C is 6. What is f dash of x for y is equal to x squared? That is 2x. That is equal to 6 if x is equal to 3, and we can see that 3 indeed does lie between 2 and 4. So this completes the chapter on differentiability. In the next video, we start working on many applications of derivatives. Thank you.